Okay, good morning, everyone. So this is the tutorial for week 4. And I believe that I have posted solution for up to question 5. So question 5, it's just Gaussian elimination. So just perform Gaussian elimination, and then you can get the LU factorization. So please read the solution, okay? And then now we do number 6. So number 6, you've seen this problem in the lab already, right? But we need to explain why, why there's a difference between the time between the two methods. So remember in the lab, we did it in the general case, right? I mean, a to the power of m x equal b, right? But here we just consider a square. And then now you see there is 2 ways to solve this problem. So one is you compute a square directly, and then you solve a square x equal b. Okay. And the other way is you solve a y equal b, then you solve a x equal y. So remember we did it in the lab, you know, a x0, ax1 equal x0, and then a x2 equal x1, and so on, right? So now we have to count the number of operations to see which one is more costly. It means that which one takes more floating operation. So let me write down on a piece of paper, okay? So you see that if you, so this is question number 6. So if you compute b equal a square, right? Then how many floating operation? So remember bij, right? Bij, you know, can be computed by the sum of a ik akj, right? You just take the row, you know, row I, you multiply by the j column, right? I mean, and you sum up from k from 1 to n. So assume that is an n by n matrix, okay? So then how many floating operation to compute bij? So to compute bij, you need how many addition? How many multiplication? So yes, well, we need n, I mean little n, yeah. So n, strictly speaking, n minus 1 addition, right? Because you add, you know, term 1 and term 2, then you got only n minus 1 addition. But then you have to multiply n times, right? You take ik multiply ikj, you have to multiply n times, so n multiplication. Yeah. So totally you need like 2n minus 1 floating operation just to compute bij. Well, yeah, n minus 1 addition and n multiplication, because you have n terms. Remember, so this multiplication you have n terms, yeah. So totally you have 2n minus 1 floating operation for only one element of bij, or one element of the matrix B, yeah. So then to compute the whole matrix B, right? Then you need how many operations? Well, you need the total number of entries, yeah, multiply with the number of flops per entries, yeah. So how many how many entries you have in the matrix B? N squared, yes, so n squared, and you multiply by 2n minus 1. So roughly it will be about 2n cubed minus n squared. But you know, I mean, you can ignore the minus n squared, right? Because if n big, so this one roughly about 2n cubed. If n is large, you know, like well, n is 1,000 or something, right? And then so now when you have the matrix B, then you need to solve B. You need to solve Bx equal little b, right? Yeah, and you can solve this by compute the LU factorization of B, right? So you can compute B equal LU, yeah, or LU. You can compute the LU factorization, or maybe you know BP equal LU, right? So this one you assume that you can have the LU factorization like this, and then it will take you about 2n cubed over 3 flops for this. Yeah, and then you have LU x equal B. Okay, so you solve U. Well, maybe you solve Ly equal B first. Yeah, so you solve Ly equal B, then you solve Ux equal Y. So this one will take n square operation. This one n square flops. Yeah. So in total, then you know you have 2n cubed here, right? So 2n cubed, right? Well, I mean, you can say that, okay, minus n square, you know, for here, and then you plus 2n cubed over 3 for here, yeah, plus 2n square. Okay, and so you can combine all the terms, and so this one will be about an cubed over 3 plus n square flops for this approach. Okay, so then you know now this is the first way to compute a square x equal b. And now if we go to the second approach, okay, so now this is the first approach. We just remember this, yeah. Now the second approach is you solve ay equal b, right? So this one, okay, again, so you can compute the LU factorization first. So compute, you know, so this is a second approach, okay? So the second approach here. So you can compute the LU factorization of the matrix A. Okay, and in this case, I just ignore the matrix B. Okay, but in general, you know, you have to have a permutation matrix B. Yeah. So this one you compute LU factorization of the matrix A, and this one takes 2n cubed over 3 flops, right? And then you solve LU. I mean LUX equal B, right, like this. So you solve Ly equal B. Well, actually, Y is not a good variable because we have Y here already. Say we solve LZ. Okay, LZ equal B, and then we solve UX equal Z. Okay, so you solve two linear system. So then this one take you n cubed flops, and this one n cubed flops. Remember we have a lower triangular system, and this one upper triangular system, linear system, right? And then now you have only ay equal b, right? So but remember we have to solve ax equal y. Yeah, so we have to solve ax equal y. Okay. Well, actually, I think I made a typo. So this one we solve ay equal b. So this one should be y. Okay, so because you replace lu equal a, so ay equal b, and so this one should be lz equal b and uy. Okay, sorry about the typo. Yeah. Okay, but now you need to solve ax equal y. So do you need to compute the LU factorization again? Do you need to compute the LU factorization again? No, right? Because you have it here already. The matrix A and the matrix U have been computed, right? So now you just go ahead and you solve, well, LUX equal Y. So now I have to label this one, say W, right? So LW equal Y. And then after that, I solve UX equal W. Okay, so I solve those two linear system. And this one takes me n square, it takes n square flops. This one n square flops. And so totally, now totally this approach, you will see that it will be 2n cubed over 3 for the LU factorization, only one, and then 4n squared flops. Okay, so now you compare with the previous approach. So the previous approach is, so now if I consider the previous approach, it will take 8n cubed over 3 plus n squared, right? And this one is only 2n cubed over 3 plus 4n squared. So you see that for small n, maybe, this one could be comparable, but for big n, for large n, then this term is the dominant term, right? So the 8n cubed over 3 is the dominant term, and this one is 2n cubed over 3 is the dominant term. So for large n, yeah, so the second approach is cost less operation than the first approach. Okay, you can see it. So that is explain why LU factorization is very helpful in speeding up the computation when you have to solve many linear system with the same matrix, yeah, and the different right hand side. Okay, so the second approach has more more efficient or less photon operation. Okay, so that is number 6. So any question? So this is okay, right? So now we move on to the next question. So question number 7. Okay, so the question number 7 is just like a counter example. Well, not a counter example, but a very interesting example of a matrix. Okay, where the determinant is fixed. Okay, is 1, but the condition number, yeah, can go to infinity. Okay, so for n go to infinity. So remember, A is just an n by n matrix. Okay, so So the whole point of number 7 is we construct a matrix, a very special matrix. Yeah? And the determinant of this matrix is fixed. Okay, but the condition number can close to infinity. Okay, and now how do we construct this matrix? So somebody has constructed this matrix and we just study this. So now we define the matrix A like this. So if you take Aij, okay, is 0, if it's a lower triangular, I mean, if the row bigger than the column, yeah, so that I is the row and J is the column index, equal 1. If I equal J, so on the diagonal, it just equal 1. And on the upper triangular, then it just equal -1. So for example, a matrix A with n equal 5 look like this. So A is, 1, 1, 1, 1, 1, yeah. And then you just have all of this one just equals 0. Okay. And on the upper triangular just equal -1. So it's very simple. Okay, so this is a matrix A. And you can see that the determinant of this matrix is 1, right? So why the determinant matrix? I mean, why the determinant of this matrix just equal 1? Why the determinant of A just equal 1? With lower or upper, take the product of on the diagonal. Yes, yes. Okay. So all the diagonal entries are just equal 1. So that's why the determinant of A is 1. Yeah. And that doesn't matter what n it is, right? N is 100. Then you take 1 to the power 100, it's still 1. Yeah. But you see now that the tricky part is to compute the condition number. You need the inverse of this matrix. Okay. And usually finding an inverse is not an easy problem. But somebody has found a way to compute the inverse of this matrix. Okay. And it is given like this. So the matrix B, I mean the matrix B, okay, the inverse of the matrix A. Somebody claimed that this matrix B is the inverse of the matrix A, where n equal 5. Okay, so B is just 1, 1, 1. I mean in the diagonal. Okay, and lower diagonal is just equal 0 as well. Okay, but now the upper diagonal. So this one is like 1, 2, 4, 8. Okay, so 1, 2, 4. So it's just a geometric sequence. Yeah. So the Bij. So the Bij is defined to be like this. So Bij is 0 if I bigger than J, the row bigger than the columns, okay, and equal 1 if on the diagonal entries, yeah. And if it's upper diagonal, then just 2 to the J minus I minus 1 if I less than J. Okay. So now we have to show that. So now the part we have to prove that B is the inverse of the matrix A. Okay, so this is we need to prove. You see, so this is the tricky part. How do we prove that B is the inverse of matrix A? So for n equal 5, you just take B, you multiply by A directly, right? You put in MATLAB or you do it by hand. Then it's easy. You can verify that. But now we need to prove it for a general n because MATLAB cannot run for infinite many n, right? So now you need to prove it. You need a theory. Yeah. So how do we prove it? So how do we prove it? So we have to prove it by the formula, right? So now suppose I just label C to be the matrix A multiplied with the matrix B, right? B times A identity or A times B, right? So this one is either way, right? So now the matrix C can be computed. I mean, suppose the entries of the matrix C is little c, right? So Cij can be computed by the formula sum of Aik. So you take the ith row, multiply with the j column of the matrix B, right? So k run from 1 to n. So somehow we have to show that C is an identity matrix, right? So now maybe we start with the diagonal first. So now suppose I just take I equal j. Yeah. Then I have Cii. It's just sum of A I K B K I from 1 to n. Yeah. So now it's not easy to see why it has to be equal 1, right? So we have to make use of the property of the matrix. K is a dummy variable. Sorry, K should be K here, not I. Yeah. K is a dummy variable. So K, I fixed it already. Okay, thank you. So now I have to sum K from AIK to BKI, right? Yeah. And now if I split the sum, now you don't see why it has to be equal 1, but let me split the sum. So I will split the sum into 3 parts. Yeah, I let K run from 1 to I minus 1. AIK BKI. And then, so now the AII now will be in a separate AII here, BI. And then I start again. K equal I plus 1 and AIK BKI. And you see that AII is a diagonal entry. BII diagonal entry. This one just one equal 1. So good. Right? But now look at this one. Look at this AIK. You know this AIK. Right? So K here is between 1 to I minus 1. So it means that the column is always less than the row. Right? So this one is the row I, right? Row I and column K. Right? And you see this row I is always big in the column. Right? And if now you go back to how you define the matrix A. So if you go back to how you define the matrix A. So if the row is bigger than the just equals 0. Okay. So the row bigger than the column just equals 0. So this one is just equals 0. Okay. And now, so if it equals 0, you multiply anything, it just equals 0, right? Now for the next term, okay, now you look at this one. Okay, so in this one, the K is the row, right? So the row, so the row is always bigger than the column, right? Because the row is and the column is I. Yeah. And you remember the matrix B, whenever the row bigger than the column, 0. Okay, so therefore, you know, this one has to be 0 as well. So you got 0 plus 1 plus 0, so it's equal 1. So it's good. So the diagonal entries is 1, right? So everything is okay. Now I consider the off diagonal of the screen is talking. It's okay for me. So well, I think maybe, you know, I mean, just wait, you know, but it's okay for me. So now everything is okay for I equal J, yeah? So audio corruption. Okay, somebody making some noise in the corridor. So okay, but at least I'm not a robot, right? So who knows? In the future, you know, they will replace me with a robot. So that's a future of education. So anyway, go back to the problem. Okay, so if I equal J, then we finish. I mean, the diagonal are 1. Now we need to show the off diagonal are 0. Okay, so now let's consider the case J less than I. Yeah. So now what is the formula? Now Cij. Okay. Again, can be, I mean, it's just a sum. Remember, we have a sum, right? From K to N, and C is just Aik Bkj. Okay. Then I want to split the sum, but now I split it in a different way. Okay, so I will split it from K from 1 to J. Okay. Aik Bkj. Then I start again. Sorry, I have to move up. I start again at K equal J plus 1 to N. Okay. Aik Bkj. Okay. So again, now I'm going to consider this one. Aik. So Aik, now you can see that K is from 1 to J. Yeah. So you see, so K is from 1 to J. So it will be less than or equal to J, right? So K will be less than or equal to J. Yeah. But then remember, J is less than I. So J less than I. Yeah. So then what does it mean? So this means that the row, remember the row is I, right? Bigger than the column. The row bigger than the column, then remember the matrix A. When the row bigger than the column, it just equals 0. Okay. And then here in this sum, you consider Bkj. Okay. So Bkj now, you see, now you have the K. Okay. is from J plus 1, so always bigger than J. So the row bigger than the column again. So therefore it equals 0. So 0 plus 0 equals 0. So everything equals 0. Okay. So that is the lower triangular part of matrix C. Okay. And it makes sense because you see the matrix A is lower, I mean the lower triangular is 0, and the matrix B, the lower triangular is 0. So when you multiply, just equals 0. Okay, so that part is reasonable. Now the hard part is the other part of the matrix. So now what happens if I less than J? So this one is J less than I, right? So now we just consider the other part of the matrix C. So now, if I consider I less than J, okay, then I'm going to write down Cij is, well, remember you have the sum, right? But now I split it in 5 terms. So sum k from 1 to I minus 1. Okay. So this one I k b k j, yeah. Then so I stop. Well, I have I then bij. Okay, so remember k run only from I minus 1 up to I minus 1. So then you have I here. Then I start again, k equal I plus 1. But now I will stop at j minus 1. Okay, so remember now I less than j. Yeah, so I k b k j. Then so this one will be I j b j j, right? Because you start at j, right? And then you start again at k equal j plus 1 to n. So this one is the last sum. Okay, so you split it into 5 terms. Okay, so now we consider this term, yeah. So this term, you see aik, right? So the row is I and the column is less than I. So row bigger than column again. So this one just equals 0. Easy, right? And the very last term. Okay, so this one k is bigger than j. Yeah. So the row bigger than the column. So this one equals 0. Okay. So now, how about the 3 terms in the middle? So now aii. So you know aii is 1, right? So you know this one, this term is just equal 1. Okay, bjj is 1. Right? The diagonal terms, yeah. Now, how about bij? So bij, well, we don't know. Bij, we don't know, right? So what is aij here? So aij here, remember j bigger than I. If you go back to so if you go back to the definition of A, yeah. So whenever the row less than the column, then aij just equal minus 1, yeah. So So now, in this case, yeah, so this one, I less than j, so this one equal minus 1, right? And this one as well, so ai k. So I and k, so k is bigger than I. Yeah, so the row less than the column, so this one equal minus 1 as well. Okay, so now we are left with, well, yes, I want to put it in, yes. So bij is, yes, it's very good. So I'm going to put it in. Okay, so now we collect on the information. Yeah, bij now is 2 to the minus j minus I minus 1. Yeah. So now we collect everything. Yeah. So this one equals 0. So this one is bij. So it will be 2 to the j minus I minus 1. Yeah. And then this one will be the minus. You can take it out. So you got bkj. Well, maybe now I replace by 2 to the j minus k minus 1, sum of k equal I plus 1 to j minus 1. Okay. And then this one is just minus 1. So now we have 3 terms left. Okay. So now let me write down a bit more explicitly. Yeah. So now I have 2 to the j minus I minus 1. And this one, if I plug it in, k is I minus 1. And I got 2 to the j minus I minus 2, right? And then I have 2 to the j minus I minus 3, right? And so on. So what is the last term? The last term is 2 to the, you put in k equal j minus 1. So j minus 1, so become j plus 1, so 2 to the 0, right? Minus 1. Yeah. So now we have to somehow we need to evaluate this term. We need to evaluate this middle one, yeah. Geometric series, yes. So this geometric series will be, you see that, it will be like 1 plus 2 plus 4 plus up to the j minus I minus 2, right? So this one will be, I mean, we put a big minus outside, yeah. And it will be 1 minus 2 the j minus I minus 1 divided by 1 minus 2, right? And then minus 1 here, and then 2 to the j minus I minus 1. Okay. And you see 1 minus 2 is minus 1. So minus, but cancel with minus. So then this one will become 1 plus 2 to the j minus I minus 1. Okay. And then you got to the j minus I minus 1 plus, sorry, this should be a minus 1. Okay, so this guy cancel with this guy, 1 minus 1, so it equals 0. Okay. So you prove it. So off diagonal are 0. So the matrix C is identity matrix. And you see, in this case, MATLAB doesn't help. Well, MATLAB just help you to prove some fixed n. But for general n, then you need a theory, right? So you need a theory. You need to know some formulas. Let's see, now it has a positive coefficient, yeah? Why don't we use the first term in the geometric series? Yeah, because it has positive coefficient, yeah. Okay, so everything is okay, right? So Okay, so that is how we prove that. So C is just identity matrix. Okay, so therefore B is the inverse of the matrix A. Okay. So now you know that the determinant is 1. Okay, so now we compute the condition number. So condition number. So now you see that the condition number, can we just say that from the hint, the columns A, B equal E, J. No, but you have to prove it, right? So I mean, still you have to prove it. So you cannot say that AB equal EJ. No, still you need to prove it. So it's not direct from the hints. You have to prove with so the jth column of a solution BJ. Yeah, but this is that you try to prove it. The hint is you need to prove it, right? Yeah. But essentially the hint is just like how you prove it. You need to prove it. Okay. Okay, so now we need to show that the condition number can grow to infinity. So now we take the norm, I mean infinity norm of the matrix A. Okay, so it will be max of in absolute value of on the rows. Yeah, so if you take the first row, all of them are just 1 in absolute value. You add it up, you got n, and the second row, you add it up, just got n minus 1, and so on. And then this one just n. Okay, and for the inverse, so B just A inverse, yeah. Then B infinity norm, it just max of on the rows, yeah. So you got 1 plus 1 plus 2 plus 2 square plus up to the n minus 2, right? And then the second one is just 1 plus 1 plus 2 plus up to the n minus 3. So definitely the first row give you the norm, right? So then it just equal 1 plus 1 plus 2 plus 2 square plus 2 to the n minus 2. And again, this one is just a geometric series again, right? So that will be 1 minus 2 to the n minus 1, and then divided by 1 minus 2, so it becomes minus 1 plus like this. Okay, so it becomes 2 to the n minus 1. Okay, so then the condition number of the matrix in the infinity norm, just the norm of A times the norm of A inverse infinity norm, so give you n to n times 2 to the n minus 1. And you see this one go to infinity when n go to infinity. Okay, so this matrix is a counterexample. I mean, not a counterexample, but it is one example to show that the condition number can go to infinity when the determinant is fixed. So it's 1, for a sequence of matrix. And now, the next question is in the opposite direction. Well, not opposite, but in another direction. So now show that there is a matrix where the determinant can grow to infinity, but the condition number is fixed. So can you do that? So give an example, okay? Give an example of a matrix A so that the determinant can go to infinity, but the condition number is fixed. Well, I mean, this one is like is an n by n matrix. Okay. So this one is when n goes to infinity. So can you think about matrix like this? Yeah, identity matrix. Yeah. So if you take identity matrix multiply with some number, okay. So suppose you take, well, I mean, just take simple, just take alpha bigger than 1, okay. Alpha identity. So this matrix, let this matrix look like this. So alpha, 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 right? Then the determinant of A is just alpha to the n. So remember alpha bigger than 1. So then this one can go to infinity when n go to infinity. Yeah. That's the condition number. So now if you look at the condition number of this matrix, condition number of this matrix will be norm of, I mean, just take infinity norm, right? Just A time A inverse, the norm, yeah. And this one just alpha, and this one just 1 over alpha. It's equal to 1 or any n. So the condition number is fixed, right? But the determinant can go to infinity. Sorry. Before alpha. This one, kappa, the condition number, sorry. Kappa. Yeah. Kappa is condition number, not a triangle. Sorry. Yeah. Okay, so that is question number 8. And then now we can go to question . So, so in some sense that, determinant can be very different from the condition number. Okay. Okay. So now we move to number 9. It's a different topic. It's about Cholesky factorization. So now in question number 9, you see that there is a matrix A equal something and L equals something and D equals something. Okay. Well, the D is just a diagonal matrix. Yeah. And the L is a lower triangular matrix. Okay, and the A is a full 3 by 3 matrix. So now by direct calculation, you can show that A is L multiplied by D L transpose. Okay, so just direct calculation. You can plug it in MATLAB or you can do it by hand. It's up to you. And now the second part is find Cholesky factorization. So you see, in general, finding Cholesky factorization is a bit tedious, but in this case, yeah. So this is the second part. Yeah. So the first part is just no. Now I'm starting to talk about question 8 part 2, right? Yeah. So now we try to find the Cholesky factorization of the matrix A. So based on this relation, so I try to find the Cholesky factorization. This means that I try to find the matrix. And this is question 9, yes? You mean question 8 part 2? Good point. So that we go back to. Sorry, I didn't talk about that. Okay, so now we have to go back to question 8 part 2. So is determinant equals 0 equivalent to near singularity? So can we use determinant to measure the condition number of A? Okay, sorry, maybe we have to go back to question 8 a little bit. Question 8 part 2, right? We haven't talked about this. Well, I mean, if you take a matrix D like this, if you take a matrix D like some beta, right? Beta, I mean on the diagonal beta, and beta are very small numbers. So suppose beta less than 1, right? Then the determinant of this matrix will be beta to the n. So beta to the n here can go to 0, right? As n go to infinity. Yeah. But the matrix D inverse is always available. So then the condition number in this case is also equal 1. So the condition number of this matrix is 1, right? So in some sense that the determinant go to 0 doesn't mean that is a singular matrix. So determinant, I mean, can get close to 0, but the matrix still invertible. So you cannot say that, I mean, the determinant is very small. It means that it's close to singularity. Yeah. So the answer is no. We cannot use the determinant to measure the condition number of A. Okay. So the answer is no. We cannot use determinant to measure the condition number. Right? In this case, I mean, the determinant close to 0, but the condition number is always equal 1. Yeah. So is it okay now? We can move to question 9. Yeah. Okay. So now we go back to question number 9. Okay. So now we try to find the Cholesky factorization of the matrix R. Sorry, of the matrix A, and we use this relation. So R transpose R equal LD L transpose. Okay. So then what is the matrix R? Should you use this relation? What is the matrix R? So what is the matrix R in this case? We have to use this relation. But directly compute R. So how do you compute R directly? Yeah, but then it's a bit, yeah, but it's a bit tedious. Well, okay, so if you write like this, so if you write R transpose R equal L square root D times square root D, okay, L transpose, yeah, and then you define this is the matrix R, okay, then you see that R transpose is just the 1/2. I mean, this is square root D. Remember, for diagonal matrix, you can take the square root by take the square root of a diagonal entries. Okay, so L transpose, the whole thing transpose, and this one become L transpose, the 1/2 transpose, and you transpose twice, it become L again, and this D is a diagonal matrix, so you transpose is still the same. So you see, so this one is exactly the matrix R transpose. Okay, so it gives you a formula to compute the matrix R directly. Okay, so it's just the 1/2 L transpose, and in our case, we know the 1/2. I mean the square root of D, we just square root 2, 1 over square root 2, and then 1. Then L transpose is just 1, 0, 0 minus 1/2, 1, 0, 1, 0, 1. And you multiply, then you get a matrix R. Yes, okay. So this way is similar, okay. And then you can show that the matrix A is positive definite. So you can show that A is positive definite by consider the definition. So you got the X transpose AX for any vector X, okay, equal X transpose RX, and this one equal RX transpose RX, and then this one just equal RX, the 2 norm square and further equals 0, right? And Rx equals 0 only when X equals 0, because R is non-singular. Okay, so therefore, you know, this is positive. So the matrix A is positive definitely. I think I have to go now because I have a lab right after this. So I have to stop the recording now, yeah.